one of the things that really makes probability interesting is the idea of independence. Without the idea of independence, probability is more or less just doing calculus, integral calculus, with functions whose total integral is 1, and which are non-negative, which is not too exciting. But sometimes random events are highly correlated. Sometimes they're unrelated or independent. And getting a way to capture that, to see that idea, is subtle and very useful. So let's see, let's just take an example. If we look at the joint PDF of x and y, say the joint PDF of x and y is uniform on the unit disk. Okay, so unit disk, good old unit disk, you know what it looks like. Looks something like that. Well, that disk has had a bad day, but in general, you know what I mean. If we were to, plot the distribution, by which I mean like draw its PDF, then we would have something like this guy here, and if we take a second copy and just move it up like that, okay, then we have there's a plot of the PDF, and so it's going to be this zone here, and I'm going to color the top in solid for no good reason I can think of. But you know what? I like purple. It's a good day for purple. Okay, so there's our PDF. And then you can see, so if it's uniform, then that's a constant value across the top. And by your knowledge of basic geometry, you know that C is going to have to be 1 over pi in order for this to work. So our joint PDF is the function so it's the function which is 1 over pi in the unit disk and 0 otherwise. And let's see, so for two random variables x and y to be independent, that means that knowing the outcome of one doesn't tell you anything about the other. So does knowing the outcome of one of these variables tell you anything about the other? It might appear not, just because it looks like it's a uniform distribution, but it's a bit subtle because, look, what happens if somebody tells you that x is equal to 1? Well, then that tells you that y has to be equal to 0, right? Or if somebody tells you that x is very close to 1, then that means you're maybe in this zone right here. Then that tells you that y has to be pretty close to 0. Well, okay, so maybe I drew it a little bit chunky there, but if we go back, let's see, and cut it a little finer, there you go, then you see that y has to be pretty close to x. Okay, so this is an example of what it looks like to be not independent. And again, maybe I'll take this somewhere else. Knowing what value the random event x took tells something about y. Or I guess perhaps I should say could tell you something about y. If somebody tells you that x is equal to 0, that actually doesn't tell you much about y at all. But if it was close to 1, then that would. So let's see. And so this is actually a surprisingly useful idea. Suppose we had like a whole slew of random variables. So suppose we had like x1, x2, all the way up to x to the 10,000. Okay, and these guys are the color values of the pixels in a 100 by 100 photo. All right, some digital picture. So the idea you should have in mind is that we've got some grid, and it's 100 by 100 pixels. So there's some grid here, and each of those little squares is a color value. So pretend that's 100 by 100, and so there's some little one right here. We'll say xj is the color of this jth pixel. So I'm just counting like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 100, and then 100, 100, 200, 300, 400, so on and so forth, right? Okay, so if you are modeling a computer program to understand how to interpret photos, so either to do signal processing on them or for some machine learning categorization type context, like you want to determine, hey, is this photo like that other photo? Or if you want to determine, hey, is this photo a picture of a plane or a kitten or a tree? Because I've already seen some photos that look like those. How do I compare? Okay, well, we have this, there's this general background underlying assumption that most of these algorithms use, which is the idea that if we have xk and xj near each other in the grid, so if xk is adjacent to xj, so like above or below or to the left or to the right, or maybe even 2 to the left or 2 to the right, something like that, nearby, then it's probably the case that xj and xk are highly correlated. And so this symbol right here is ill-defined. It's nothing precise. I'm just saying is kind of like, right? So, but this is called the continuity assumption, and it underlies, like I said, most of the algorithms that run machine learning for setting up neural networks and other kinds of things as well. Ask me about it, by the way, if you're interested, because I love talking about this stuff. So let's see. So the opposite of this highly correlated idea is if they're independent. So x and y are said to be independent random variables if and only if their joint probability distribution or probability density function can be written as a function, we'll call it f1, of x only times a function, we'll call it f2, of y only. So it's this thing we saw again when we talked about Fubini theorem, that it factors and splits into two different things. And so for like an example of something where you would expect x and y to be independent random variables, maybe x is the price of corn on the commodities market, and y is the price of Tesla. I mean, you really wouldn't expect those the price of one to be correlated with the price of the other at all. So let's see. So what's a case in which this kind of thing comes up in a practical yet simple to model situation? Suppose we install 2 light bulbs. It's a reasonable assumption that the lifetimes of these bulbs are independent. If one was defective, it doesn't necessarily mean the other one is defective. Assume that the factory is a fairly decent factory. So we can ask the question, how long until both of these functions burn out? When are they both dead? Right? So when one dies, it shouldn't affect whether or not the other one is going to die. That's something that has to do with the, when it was manufactured in the first place. So let's see, if 1 year is the average lifetime of a bulb, then it's standard to model lifetimes and waiting times, things like that, with exponential distributions. And so if we take this to be 1 to be the average, then our lambda would equal 1, and we just have e to the minus x. And since we're looking at the joint distribution of x and y, we've got actually that this is going to be an exponential in x times an exponential in y. And from our previous example, we saw that the normalizing constant for such a function is going to be 2. So that's going to be the joint PDF for these two. So notice that this one factors as a function of x times a function of y only. All right, so now let's see. So the probability that both are dead in say within 6 months is, let's see, so that's going to be the probability that the maximum of the two is less than or equal to half a year. 6 months is half a year. And so for them both to be under that value, that means that's the same thing as saying that the larger of them is. And so let's see, so what does that look like as an integral? So we need to figure out how to set this up. Maybe it's actually a red herring to say max. It would be equivalent to think of it this way. Maybe this is simpler. Either way, you can see that this means that we're looking at the rectangle from 0 to 1/2, 0 to 1/2. And then we've got our joint PDF. And it actually doesn't matter what order I write those in because everything in this particular example is completely symmetric. And so let's see, so I can pull out the 2, and then I have 0 to 1/2 e to the minus x dx. And then I'm going to multiply that by another integral that looks exactly the same, except it has a dummy variable of y instead of x. So to save space in ink, I could just call it that one. Just change the dummy variable. And then let's see, so we will work out that integral and see that it comes to 1 minus e to the negative 1/2 quantity squared. And your pocket calculator will tell you that this is something like 0.3096. So basically a 31% chance that they're both dead in the first 6 months. So independence is, like I said, nuanced, rich, tricky, and actually kind of a deep idea. But when you're working out integrals, actually all that it boils down to is the fact that you can use this shortcut right here, where you take the double integral of f1 of x, f2 of y, and write it as the product of the two single integrals, one with respect to x and one with respect to y.